Imagine two slides side by side, dropping from the same high point to the same low one. One is a straight ramp, the other bends steeply down at the start, then flattens out. Release a marble on each at once. The curved one wins, even though its marble travels farther. In 1696, that puzzle became a public challenge aimed at Isaac Newton, who solved it overnight and refused to sign his name. But here is what nobody tells you. The method invented to settle it turned out to be the deepest rule in physics. A single line that reproduces Newton's laws: light, electricity, relativity, gravity, and every particle we have ever found. It has not failed once in 280 years, and nobody can explain why it is true. By the end of tonight, you will know exactly what that rule is, and where the explanation runs out. Before we begin, if following one strange idea all the way down is how you like to drift off, a quick like or subscribe really helps the channel grow. It means a great deal to me. Now, let's ease in. There is a question so simple that it sounds like it belongs in a classroom, and it does not have a simple answer. It took the best minds in Europe the better part of a century to settle it, and settling it opened a door that physics has been walking through ever since. Here is the question. Take 2 points, put one of them higher than the other, and offset it sideways, so that they are not stacked vertically and not lying flat. Now build a ramp between them, a perfectly smooth ramp with no friction at all. Put a small bead at the top and let it go. Gravity does the rest. What shape should the ramp be, so that the bead arrives at the bottom point in the shortest possible time? Most people answer immediately, and most people answer the same way. A straight line. The straight line is the shortest distance between 2 points. Everyone knows that. And if you want to get somewhere fast, you take the short way. It is the answer that feels like it cannot be wrong. It is wrong. Think about what the bead is actually doing on a straight ramp. It starts at rest. It has to accelerate, and on a gently sloping straight ramp, it accelerates gently, which means it spends the early part of the journey moving slowly. All of that time at low speed is time being wasted. Now imagine bending the ramp down at the beginning, making it steep, almost vertical for the first stretch. The bead drops. It picks up real speed almost immediately, and then the ramp curves out and flattens and carries it across to the finish, at a speed the straight ramp never gave it. That curved ramp is longer. The bead travels farther, and it still wins, because it spends most of its journey moving quickly instead of most of its journey building up to quick. So now the question sharpens into something much harder. If bending the ramp down helps, how much should you bend it? Bend it too little, and you have wasted the advantage. Bend it too much, and the bead plunges almost straight down, gets very fast, and then has to crawl sideways along a long, flat run to reach the finish. There is a trade-off between the length of the path and the speed you can reach early, and somewhere in the middle of that trade-off, there is one exact shape that balances the two perfectly. Which shape? That is the whole problem, and there is something deeply awkward about it that is worth naming right at the start. When you look for the largest number in a list, you can check every number in the list. When you look for the tallest person in a room, you can look at every person in the room. But when you look for the fastest ramp, you are searching through every possible curve that connects 2 points. Not 100 of them, not 1,000,000. An unlimited, unlistable infinity of curves, most of which have no names, no equations, and no reason to exist except that they happen to connect the same 2 points. You cannot check them one at a time. You cannot check even a vanishing fraction of them. And yet the problem clearly has an answer, because if you build the ramps and release the beads, one of them clearly wins. This problem is called the problem of fastest descent. The formal name for the winning curve, when it was eventually found, came from Greek. Brachistos means shortest. Chronos means time. The curve of shortest time. The brachistochrone. The first serious attempt on it belongs to Galileo Galilei, and it appears in the last book he ever wrote. He was old, blind, and under house arrest outside Florence when he finished it, and it was smuggled out of Italy and published in Leiden in 1638 under the title Discourses and Mathematical Demonstrations Relating to Two New Sciences. Deep in the section on falling bodies, Galileo takes up the question of descent along different paths, and he proves something genuinely correct. He shows that an arc of a circle beats the straight chord. He shows that it also beats any many-sided chain of straight segments you care to inscribe. And then he draws the conclusion that anyone would have drawn. If the circle beats the straight line, and the circle beats every polygon he can construct, then the circle must be the answer. It is not the answer. And the reason it is not the answer is the most instructive part of the whole episode, because Galileo did not make an arithmetic mistake. He made a mistake about what kind of question he was asking. He compared the circle against a handful of named competitors, found that it beat all of them, and generalized. But beating everything you thought to test is not the same as beating everything. Out in the unlisted infinity of curves that Galileo never thought to write down, there was one doing better, and no amount of care with the competitors he had chosen was ever going to find it. That is the shape of the difficulty. To answer a question like this properly, you need a method that does not work by comparison at all. You need a method that can reach into an infinite family of possibilities and pick out the best member without ever examining the others. In 1638, no such method existed anywhere in mathematics. Calculus itself was still 50 years away. So the question sat there, and when the method finally arrived, it did not just solve the problem of the ramp. It turned out to be the deepest thing anyone has ever found out about how the physical world operates. I want to plant one sentence now, before you know what it means, because everything that follows is going to keep returning to it. The sentence is this: for any motion you care to describe, there is a number attached to the whole journey, and the journey that actually happens is the one where that number stops changing. That is it. That is the rule. It sounds like almost nothing. It does not mention forces. It does not mention pushing or pulling or attraction. It does not mention mass or energy or fields or particles. It is one condition applied to one number, and from it you can derive Newton's laws of motion, the behavior of light, the equations of electricity and magnetism, special relativity, general relativity, and the whole of modern particle physics. Every one of them, not as analogies, as mathematical consequences. Physicists have been using this rule for 280 years. It has never once failed. It is, without exaggeration, the closest thing our species has to a single unifying law of nature. And nobody knows why it is true. Not in the sense that the mathematics is uncertain, because the mathematics is airtight. Not in the sense that the predictions are shaky, because the predictions are the most precisely confirmed in all of science. In the sense that when you ask where this rule comes from, why the number is the number it is, and what it means that the universe should obey it at all, physics does not have an answer. It has never had an answer. The people who built it did not have an answer. The people who use it today, in every physics department on the planet, do not have an answer. By the end of tonight, you will understand exactly what that number is, exactly how it produces every law we have, and exactly where the explanation runs out. And I want to be honest with you about that last part from the beginning, because the ending of this story is not a resolution. It is a very precise description of a whole. But we are getting ahead of ourselves, because in the 1696s, nobody was thinking about the structure of reality. They were thinking about a ramp, and about a challenge, and about who could solve it faster than whom. The man who was about to set that challenge was one of the most gifted mathematicians in Europe, and one of the least pleasant. He came from a family that argued about mathematics the way other families argue about money, and he had already worked out the answer to the problem of fastest descent before he told anybody it was a problem. He did not publish his solution. He published the question. In June of 1696, a notice appeared in a journal published in Leipzig called Acta Eruditorum. The journal had been founded by Gottfried Wilhelm Leibniz, and it was where the mathematicians of Europe went to read what the other mathematicians of Europe were doing. The notice was a challenge, and it was signed by Johann Bernoulli. Bernoulli invited the mathematicians of the world to find the curve of fastest descent. He described the problem carefully. He noted that the answer was not the straight line, and he gave everyone 6 months. He already had the solution. That is the part worth holding on to. He was not asking because he needed help. He was asking because he wanted to see who else could do it, and more particularly, he wanted it on the record that he had done it first. The Bernoullis were a remarkable family, and a difficult one. Johann's father had forbidden him to study mathematics and pushed him toward business, and Johann had studied it anyway, in secret, and was thrown out of the house for it. He spent decades in open competition with his own older brother Jakob, each of them publishing solutions to problems the other had posed, each accusing the other of theft. Much later in life, he would be accused of plagiarizing the work of his own son. He was, by every account that survives, brilliant, generous to students, and completely unable to let a competition go. So the challenge went out, and 6 months passed, and nothing came back. Not one submission. At this point Leibniz, who was a friend of Bernoulli's, and who had been following the whole thing with interest, suggested that the deadline be extended. His stated reason was that foreign mathematicians had not had a fair chance, that the journal took time to travel, that the news had not reached everyone, that it would be more sporting to give until Easter of the following year. Bernoulli agreed. The word doing the real work in that sentence is foreign. Leipzig was where the challenge was published. Leibniz was in Hanover. Bernoulli was in Groningen. Everyone involved understood perfectly well which particular foreigner had not yet been heard from, and everyone understood that the challenge had been aimed at him from the beginning. There was also something larger going on underneath, and it is worth knowing about, because it explains the temperature of the whole affair. Leibniz and Newton were at that moment locked into the ugliest priority dispute in the history of mathematics, over which of them had invented calculus. Each had developed it independently. Each had supporters who accused the other of theft. The quarrel would eventually consume both men, poison relations between English and continental mathematics for a century, and leave English mathematics, using Newton's clumsier notation, out of loyalty, long after the continent had moved on. So when Leibniz suggests extending a deadline so that a certain foreigner has time to reply, it is not simply courtesy. A public challenge that only continental mathematicians can solve would be a very useful thing for the continental side to have. The brachistochrone problem was sitting inside a much bigger fight, like a duel, arranged inside a war. Isaac Newton was 54 years old, and he was not doing mathematics anymore. That fact is stranger than it sounds now, because from where we are standing, Newton is the mathematician, the towering figure, the author of the Principia. But by 1696, that book was 9 years behind him. He had suffered what appears to have been some kind of breakdown in the early 1690s, and he had left Cambridge for London and taken a job. The job was Warden of the Royal Mint, and it was not ceremonial. England was recoining its entire currency, melting down the clipped and debased silver of a century and striking it fresh, and Newton was running a substantial part of that operation. He was also, personally and with evident enthusiasm, hunting counterfeiters. He ran informants through the taverns of London. He interrogated suspects himself. Within 3 years, he would secure the conviction and hanging of the most successful forger in England. He was busy, he was tired, and he had put the mathematics down. Let me put you in the room. It is the late afternoon of the 29th of January, 1697. In London, in late January, it is already dark by 4, and the house on Jermyn Street is cold, in the way that houses were cold before central heating, which is to say, cold everywhere except directly in front of the fire. Newton has spent the day at the Mint on Tower Hill, among the presses and the assay furnaces and the ledgers of a national recoinage, and he has come home. He is 54. His hair has gone white. There is post waiting for him, and among it there is a letter from Groningen. He opens it. It is a mathematical challenge, addressed to the sharpest minds in Europe, with a deadline attached. Whatever else Newton was, he was not a man who enjoyed being tested. The following day, he wrote to Charles Montague, the Chancellor of the Exchequer, and his line about it has survived exactly. He said, "I do not love to be dunned and teased by foreigners about mathematical things." He is annoyed. He says so plainly. And then, having said so, he sits down at the table, with the letter in front of him, and he starts working, because the problem is too interesting to leave alone, and he does not stop. The candles burn down, the house gets colder. Outside, London is silent in the way a 17th century city is silent at night. And at 4 o'clock in the morning, Isaac Newton, who has not done serious mathematics in years and who spent the day chasing coin clippers, has the answer. Johann Bernoulli, who set the problem and who had every advantage, had taken 2 weeks. What Newton did next has been read 2 different ways ever since. He wrote up his solution, sent it to the Philosophical Transactions of the Royal Society, and did not sign it. It was presented to the Society on the 24th of February, 1697, anonymously. One reading is modesty. The other reading, which I find more persuasive, is contempt. Bernoulli had constructed an entire public performance around the question of who was the better mathematician. Refusing to put your name on the answer is a way of refusing to play, and it is a considerably more cutting move than winning openly would have been. Bernoulli read the anonymous solution, and the remark he made about it has outlived almost everything else he ever said. In Latin, tanquam ex ungue leonem, as the lion is known by its claw, he meant that the signature was unnecessary. You do not need to be told who wrote this. There is one person in Europe who thinks like that, and you can identify him from a single piece of his work, the way you can identify a lion from a single print in the mud. It was an insult wrapped inside a compliment, or a compliment wrapped inside a surrender, depending on how generous you are feeling toward Johann Bernoulli. Hold on to that phrase. We are going to need it again, much later, in a context Bernoulli could not have imagined, when it stops being about one man's handwriting and starts being about something much larger. In total, 5 solutions came in. Newton's, Johann Bernoulli's own, his brother Jacob's, Leibniz's, and one from the Marquis de l'Hôpital. 5 of the best mathematicians alive, all arriving at the same answer by different routes. And the answer, when they all converged on it, was not the circle. It was a curve nobody would have guessed by looking at the problem. A curve that already had a name and a reputation and 60 years of vicious priority disputes attached to it. It was the shape traced by a single point on the rim of a rolling wheel. But the answer matters much less than one of the methods used to reach it. Newton's solution was the fastest and the most impressive. Jacob Bernoulli's was the ugliest, and it turned out to be the one that mattered most. Jacob attacked the curve the way you might attack a rope, by cutting it into tiny pieces and asking what has to be true of each piece if the whole thing is optimal. It is slow, graceless work. It also contains the germ of the correct general method, because it is the first time anybody treats the shape of a curve as the thing being varied, rather than a number. Half a century later, that idea would become an entire branch of mathematics, and the brothers, who never reconciled, would both be dead before anyone realized which one of them had opened the more important door. And Johann's own solution, the one he had been sitting on since before he posed the challenge, was something else again. It was not really a solution to a problem about falling. He had solved it by refusing to treat it as a mechanics problem at all. He had solved it by turning the bead into a ray of light. To understand why that was possible, and why it was the single most consequential move in this entire story, we have to leave the ramp alone for a while and go back a good deal further, to a question about why a stick looks broken when you put it in water. If you have ever dropped a coin into a swimming pool and reached in to pick it up, you have felt this problem in your hands. The coin is not where it appears to be. You look down through the water, you see it clearly, you reach for exactly that spot, and your fingers close on tile. The coin is somewhere slightly else, and it is somewhere slightly else for a reason that turns out to sit at the root of everything we are talking about tonight. The first person we know of to think carefully about how light chooses its route was Hero of Alexandria, working in Egypt in the 1st century of the Common Era. Hero was an engineer and an inventor, the man who built the first recorded steam device and a set of automatic temple doors, and among his written works is a treatise on mirrors called the Catoptrics. In it he makes a claim about reflection that is both correct and, for its time, extraordinary. When light bounces off a mirror on its way from a source to an eye, it takes the shortest available path, not a short path, the shortest one. You can test this yourself on paper. Put a lamp on the left, an eye on the right, and a flat mirror below them both. Draw any path you like that leaves the lamp, touches the mirror somewhere, and arrives at the eye. Now measure it. The path you drew will be longer than the one where the angle coming in equals the angle going out, unless you happen to draw exactly that one. That familiar schoolroom rule, angle of incidence equals angle of reflection, is not a separate fact about mirrors. It is the geometric consequence of taking the shortest route. So in a single uniform medium, light appears to be economizing on distance. That is a strange thing to find in nature, and Hero seems to have understood that it was strange. He wrote about it in terms of nature doing nothing in vain. Then somebody looked at water, and the picture broke. When light crosses from air into water, it does not continue straight. It bends toward the perpendicular, and the bent path is demonstrably not the shortest way between where it started and where it ends up. A straight line between those same 2 points would be shorter. It is right there. You can draw it. Light does not take it. This is why the coin is not where you think. The light leaving the coin bends as it exits the water, and your eye, which has no way of knowing that a bend happened, traces the ray backwards along a straight line and places the coin along that line instead. It is why a spoon in a glass appears snapped at the surface, why a pond looks shallower than it is, and why spearfishing requires you to aim somewhere other than at the fish. For roughly 1600 years, people worked on describing this bend precisely, and eventually they got it. The rule is this: take the angle the incoming ray makes with the perpendicular, and take the angle the outgoing ray makes with the perpendicular, and compute the sine of each. Divide the first by the second. That ratio is a fixed number that depends only on which 2 substances are involved. Air and water always give the same number. Air and glass always give a different one. Same materials, same number, every time, at every angle. The history of who found it is a small scandal of its own. A Persian mathematician named Ibn Sal, working in Baghdad around the year 984, wrote down an equivalent construction in a treatise on burning mirrors and lenses, and used it to design lens shapes that focus light cleanly. Thomas Harriot in England had the rule by 1602 and never published. Willebrord Snellius in the Netherlands derived it around 1621 and never published. René Descartes published it in 1637. In English, it is called Snell's Law, after the man who found it third and told nobody. So by the middle of the 1600s, the rule was known, it was accurate, and it worked. And nobody could say why it was true. It was a number that came out of experiments. There was no reason attached to it. It was, in the exact sense, a brute fact. The man who broke that open was not a physicist and did not consider himself one. Pierre de Fermat was a lawyer. He was a councillor at the Parliament of Toulouse, which meant that his days were spent hearing cases and issuing judgments, and by all accounts he was conscientious about it. Mathematics was what he did afterwards. He would come home, spend the evening with his wife and children, and then work on problems for pleasure, and he almost never published any of it. Most of what we have from him survives in letters to other mathematicians, and one of the most famous things he ever wrote was a note scribbled in the margin of a book claiming he had a proof that would not fit in the space available. That claim took 357 years to verify. Fermat looked at Hero's idea and thought that the instinct was right and the quantity was wrong. Nature, he suggested, is not economizing on distance. Nature is economizing on time. Now watch what that single substitution does, because it is one of the most elegant moves in the history of science. In a single uniform medium, light travels at a constant speed, so the fastest path and the shortest path are the same path, and Hero's result survives untouched. Reflection still obeys equal angles. Nothing is lost. But at the surface of water, everything changes, because light does not travel at the same speed in water as it does in air. It is slower in water, and the moment the two speeds differ, the shortest path and the fastest path come apart. There is a version of this you already understand intuitively. Imagine a lifeguard on a beach, and a swimmer in trouble out in the water, and the swimmer is not directly out in front, but off at an angle down the shore. The lifeguard can run fast on sand and can only swim slowly. What is the quickest way to reach the swimmer? Not the straight line. The straight line spends too much of the journey in the slow medium. The quickest route runs farther along the beach than a straight line would, entering the water at a point that shortens the swim at the cost of a longer run. The path has a kink in it, and the kink is at the water's edge. That is exactly what light does. The bent path is longer in total, and it is faster, because it trades distance in the fast medium for distance in the slow one. Fermat suspected all of this by around 1657, and did not do the calculation, because he expected it to be horrible. To check it properly, he would have to consider every possible point at which the ray could cross the boundary, compute the total travel time for each one, and then demonstrate that the crossing point light actually uses is the one that makes that total smallest. It is exactly the kind of search through everything problem we ran into with the ramp, and Fermat's own view of it was that even if he could grind it out, the answer would come out too ugly to be worth having. 5 years later, he changed his mind and did it anyway. Snell's law came out. Exactly. Not approximately, not as a good fit. The precise relationship, signs and all, dropped out of the assumption that light minimizes travel time. And that mysterious constant, the number that had been measured for centuries with no explanation attached to it, turned out to be nothing more mysterious than the ratio of the two speeds. The speed of light in the first medium divided by the speed of light in the second, which means Snell's law can be rewritten in a form that is almost embarrassingly clean. The sine of the angle divided by the local speed of light is the same on both sides of the boundary. Fermat wrote to a correspondent about it on the 1st of January, 1662. He called it the most extraordinary, the most unforeseen, and the happiest calculation of his life. He had every right to. So far as anyone can establish, this is the first moment in the history of science when a law of nature was derived from an optimization, from the assumption that out of all the things nature could do, it does the one that makes some quantity as small as possible. Every optical phenomenon known in Fermat's lifetime falls out of it. Light traveling straight, light reflecting, light refracting, lenses, all of it, from one sentence about time. And roughly 35 years later, a furious Swiss mathematician in Groningen with a ramp problem to solve, looked at Fermat's principle of least time and realized that a bead sliding down a curve and a ray of light crossing into water were, if you squinted correctly, the same object. Johann Bernoulli's solution to the problem of fastest descent begins with an observation so simple that it is easy to walk straight past it. A bead sliding down a frictionless ramp gets faster as it goes down. A ray of light crossing into a thinner medium gets faster as it crosses. Both of them are objects moving through a region where the available speed changes as you go. And Fermat had already worked out exactly what a moving thing does when the available speed changes as you go. So Bernoulli stopped thinking about gravity altogether. He replaced the bead with a ray of light, and he replaced the ramp with a stack. Picture the vertical space between the starting point and the finishing point sliced into thin horizontal layers, like the pages of a book lying flat. Each layer is a different optical medium, and each one is slightly less dense than the layer above it, which means light moves slightly faster in each layer than in the one before. A ray entering the top of the stack refracts at the first boundary and bends. Then it hits the second boundary and bends again. Then the third. It descends through the stack as a staircase of straight segments, kinked at every interface, bending a little more each time as it accelerates. Now make the layers thinner, then thinner again. In the limit where the layers have no thickness at all, and there are infinitely many of them, the staircase stops being a staircase and becomes a smooth curve, and Snell's law is being obeyed continuously at every single point along it. That is the whole trick. Bernoulli has converted a question about a falling object into a question about a bending light ray, and the light ray question already has an answer. One thing remains to be fixed. If this fake light ray is going to mimic a real falling bead, its speed has to change in exactly the way a falling bead's speed changes. So how does a falling bead's speed change? Conservation of energy answers it in one line. As the bead descends, it loses height and gains speed, and the potential energy it gives up turns entirely into kinetic energy, because there is no friction to take a cut. So the kinetic energy at any moment equals the potential energy given up to get there. Kinetic energy is 1/2 the mass times the speed squared. Potential energy given up is the mass times the strength of gravity times the height dropped. Set them equal, and the mass cancels off both sides, which is why a heavy bead and a light bead do exactly the same thing. What is left says that the speed squared is proportional to the distance fallen, or, turning it around, the speed of the bead is proportional to the square root of how far it has dropped below its starting point. So Bernoulli needs a fake medium in which the speed of light, instead of being constant, grows like the square root of the depth. Fine. That is just a rule for building the stack. Now apply Snell's law at the first boundary between layers. The sine of the incoming angle divided by the square root of the depth of the first layer equals the sine of the outgoing angle divided by the square root of the depth of the second. Here is the key move, and it is the reason this solution is beautiful rather than merely clever. Snell's law does not only hold at the first boundary, it holds at the second one too, and at the second boundary, the ray coming in is the same ray that went out of the first, so that same combination, sine of the angle over the square root of the depth, has to have the same value at the second boundary as at the first, and the third, and the fourth, all the way down, which means that along the entire curve, from the release point to the finish, the sine of the local angle divided by the square root of the local depth is a constant. It never changes. Whatever value it has at the top, it has everywhere. That single statement is a differential equation, and it is the equation of a curve that was already extremely famous in 17th century mathematics. It is the cycloid. A cycloid is what you get if you paint a dot on the rim of a bicycle wheel. and roll the bicycle along a flat road and trace the path of the dot through the air. It sweeps forward and up, arcs over, comes down, touches the road, and starts again. It is a shape everyone has seen without noticing. For the ramp, you flip it over. Imagine the wheel rolling along the ceiling, and the painted dot hanging below it, tracing an arch that dips down and comes back up. Cut a section out of that arch, run a bead down it, and you have the fastest slide that can exist between those 2 points. Not a straight line, not a circle, the path a dot on a rolling wheel would take. I want you to ride it for a moment. You are at the top, on the bead, and the release is more like being dropped than being let go. The track under you falls away almost vertically, and for a beat, you are not sliding at all. You are simply falling, with the curve running just beneath your feet. Speed arrives fast, faster than it feels like it should. Then the curve begins to open. It flattens under you, and the falling turns into traveling, and now you are being carried sideways across the bottom of the arch at a speed no straight ramp could have handed you in that distance. There is no moment where you fight the shape. It is not steep where you need speed and not shallow where you need distance. It simply gives you the fall first and spends it afterwards. And by the time a bead on the straight ramp beside you is still working its way patiently down, you have already arrived. And now the second demonstration, which is the one that unsettles people. Line the same arch with 100 beads. Put one at the very top, one halfway down, one near the bottom, and the rest scattered between them, at whatever heights you like. Release all of them at the same instant. They all reach the bottom together. Not approximately, exactly. The bead released from 3 centimeters above the base, and the bead released from the very top of the arch, arrive at the same moment, because the one from higher up has farther to travel and gets correspondingly faster, and on this particular curve, those 2 effects cancel each other out perfectly. Nothing else does that. On a circle, it does not work. On a straight ramp, it does not work. On this curve, the time to the bottom does not depend on where you start. This property was already known. Christian Huygens had proved it in 1659 and published it in 1673, and he had a practical reason for caring. A pendulum swinging in the ordinary way along a circular arc does not quite keep constant time. The period depends slightly on how wide it swings, which is a serious problem if you are trying to build a clock accurate enough to determine longitude at sea. Huygens realized that a pendulum forced to swing along a cycloid instead of a circle would be perfectly regular, regardless of how far it swung, and he built clocks with curved metal cheeks at the pivot to bend the string into a cycloidal path. On land, they were marvels. At sea, they failed, defeated by friction and the motion of the ship, and the longitude problem had to wait another century for John Harrison to solve it a completely different way. So the curve had a name and a reputation. In the 17th century, the cycloid was nicknamed the Helen of geometers, because of how many bitter arguments broke out over who had discovered which of its properties. Roberval, Torricelli, Descartes, Pascal, and Fermat had all fought over it. But nobody had expected this. The curve that makes descent fastest, and the curve on which every starting height gives the same descent time, are the same curve. 2 questions from what look like 2 different subjects, and one shape answers both. Bernoulli noticed, and wrote it down with obvious satisfaction. In this way, he said, I have solved at one stroke 2 important problems, an optical one and a mechanical one, and have achieved more than I demanded from others. I have shown that the 2 problems, taken from entirely separate fields of mathematics, have the same character. He thought he was making a remark about 2 problems. He was making a remark about the whole of physics, and it would take another 50 years, one more mathematician, and a public humiliation before anyone understood that. About 40 years after the Brachistochrone, one of Johann Bernoulli's own students asked a question that nobody else seems to have thought to ask. And it is the question that turns this whole story from a set of clever mathematical tricks into a claim about the universe. Pierre-Louis Moreau de Maupertuis was a French mathematician with an unusual career. Before any of this, he had led an expedition to Lapland in 1736 and 1737 to measure the length of a degree of latitude near the Arctic Circle. The point of the trip was to settle an argument about the shape of the Earth. Newton's theory predicted that a spinning planet should bulge at the equator and flatten at the poles. The Cassini family in France insisted the opposite, that the Earth was stretched along its axis like an egg. Maupertuis went north, took the measurements in appalling conditions, came back, and demonstrated that Newton was right. Voltaire, who was a friend at the time and enjoying himself, started calling him the great flattener of the Earth. So this was a serious man with a real reputation, and what he noticed was this. Light refracts. Particles, in certain situations, behave in ways that look mathematically similar. Fermat had explained light's behavior by saying that light minimizes the time it spends traveling. But why time? Maupertuis could not construct any argument for it. Time is not conserved. Time is not exchanged between objects. Time is not a substance the universe possesses a limited quantity of. If nature is economizing on something, why on earth would it be economizing on that? His guess was that Fermat's principle was a special case of something deeper, and that the deeper quantity would govern light and matter alike. So he proposed one. He called it the action. In his formulation, the action for a moving object is its mass, multiplied by its velocity, multiplied by the distance it travels. Heavier means more action. Faster means more action. Farther means more action. If a journey has several stages, you compute mass times velocity times distance for each stage and add them together. And his claim was that out of every path a system could conceivably take, the one it actually takes is the one for which that total is as small as possible. Let me do a toy example so the quantity stops being abstract, because it is genuinely easy to compute. Take a ball weighing 1/2 kilogram, roll it across a smooth floor for 6 meters at 3 meters per second. The action for that stretch is 1/2 times 3 times 6, which is 9. The units are kilogram meters squared per second, and hold on to that phrase because we are going to come back to it in a way you will not expect. Now suppose the ball hits a wall, bounces, and comes back 6 meters at the same speed. That is another 9. Total action for the round trip, 18. Maupertuis' assertion is that if you consider every possible way the ball could have gone from its starting point to its ending point, bouncing off the wall higher up, bouncing lower down, taking a wider path, taking a stranger one, the route reality selects is the one that makes that total the smallest it can be. He announced this at the Paris Academy of Sciences on the 15th of April, 1744, in a paper about the agreement between laws of nature that had previously seemed incompatible. 2 years later, he broadened it into a general principle covering motion and rest together, and he summed the whole thing up in a sentence that has followed him ever since. This action, he wrote, is the true expense of nature, which she manages to make as small as possible. Now, how was this received? He was attacked, he was ridiculed, and then, worse than either of those, he was ignored. Some of the attack was legitimate, and it is worth being honest about that, because Maupertuis was reaching further than his evidence allowed. There was no argument anywhere in his papers for why the quantity should be mass times velocity times distance. Why not mass times velocity squared times distance? Why not mass times the square root of velocity? There are infinitely many combinations you could write down, and Maupertuis had essentially picked one out of the air because it felt right and because it produced the correct answers in the handful of cases he checked. He had worked examples. He did not have a proof. And there were two conditions his principle actually required in order to be true, which he had not noticed at all, and without which the whole thing is simply false. He also wrapped it in theology, which did him enormous damage. To Maupertuis, a universe that economized was evidence of a designer choosing the most efficient possible world. Later physicists inherited his mathematics and threw the theology out of the window, but the association lingered, and it made the principle smell to many people like metaphysics wearing a lab coat. That was the fair criticism. What happened next was not fair at all. In 1751, a man named Samuel Koenig published a challenge. Koenig was a former friend of Maupertuis, a serious scholar of Leibniz who had spent years working through the Leibniz archives in Hanover. He claimed two things at once: that the principle was wrong and that Leibniz had thought of it first. He cited a letter, supposedly written by Leibniz in 1707, describing something very similar. Koenig could not produce the original. He had, he said, a copy. The Berlin Academy of Sciences, of which Maupertuis was president, and where Leonhard Euler led the investigation, declared the letter a forgery in 1752. The original has never been found to this day, and most modern historians think Koenig believed it was genuine and that the Academy's handling of the affair was indefensible regardless of the letter's status. And then Voltaire arrived. Voltaire was the most famous writer in Europe and one of the most effective destroyers of reputations who has ever lived. He had been Maupertuis' friend. By 1752 he was not, for a tangle of reasons that included genuine intellectual disagreement, court politics in Berlin, and persistent rumors about Maupertuis and Voltaire's lover, Émilie du Châtelet. Voltaire wrote a pamphlet. It was called The Diatribe of Dr. Akakia, native of Saint-Malo, and it was 32 pages of sustained, precise, gleeful mockery, portraying Maupertuis as a pompous fool whose great principle was gibberish. The name Akakia is itself a joke. It was extremely funny, and that is exactly why it worked, because a serious rebuttal can be answered, and a joke cannot. Frederick the Great, King of Prussia, who had brought Maupertuis to Berlin to run his academy, and who was also Voltaire's host, had copies of the pamphlet publicly burned. Voltaire was held for several weeks and then expelled from Prussia altogether. None of that helped. Burned pamphlets circulate. They always circulate. The quieter damage came from a different direction. Denis Diderot and Jean-Laurent d'Alembert were at that moment assembling the Encyclopédie, the great catalogue of Enlightenment knowledge, and they treated Maupertuis' principle with open skepticism. That is a much heavier blow than satire, because satire tells everyone a thing exists, and encyclopedias tell everyone whether it is worth their attention. Between the forgery scandal, the pamphlet, and the reference works, the principle of least action was effectively removed from serious French natural philosophy for a generation. It was not refuted, it was filed under embarrassing. And Maupertuis, who was not a young man and whose health was failing, had to watch it happen. He had told people that the principle of least action was the thing he expected to be remembered for. Not the shape of the earth, not the Lapland expedition, not any of the rest of it. This, the one idea he thought would outlast him. Instead, he spent the last years of his life being described across Europe as a plagiarist, an idiot, and a joke. He left Berlin. He went south, and he died in Basel in 1759 in the house of Johann II Bernoulli, the son of the man who had taught him. He died believing that the idea had destroyed him. He was right about the idea. The quantity he guessed at, mass times velocity times distance, is the correct one. It is in every graduate physics textbook printed today. It is called the abbreviated action, and it is still attached to his name, and it is the same quantity that runs through quantum mechanics, general relativity, and the standard model of particle physics. He could not prove it. He could not justify it. He picked it out of the air. and the air handed him the organizing principle of the physical universe. There is a distance in this story between being right and being believed, and Maupertuis died inside that distance. It closed about a year after he was buried, and it closed because of two men who had been quietly working on the problem the entire time, one of whom was the greatest mathematician of the age, and one of whom was a self-taught 19-year-old writing letters from Turin. Through all of it, the forged letter, the burned pamphlets, the encyclopedia entries written in that particular tone people use when they want you to know something is not respectable, one man defended the principle of least action without hesitation. He happened to be the most capable mathematician alive, and possibly the most productive human being in the history of the subject. Leonhard Euler published a book in Lausanne in 1744, the same year Maupertuis made his announcement in Paris. Its Latin title translates roughly as a method for finding curved lines, enjoying some property of maximum or minimum. It is not a book about physics. It is the founding document of an entire branch of mathematics, the calculus of variations, and it exists because Euler wanted to be able to answer questions of exactly the kind the brachistochrone had posed, in general, rather than one clever trick at a time. Euler did three things to Maupertuis' principle, and each of them was necessary. The first was to replace the sum with an integral. Maupertuis' action was a sum, mass times velocity times distance for this stretch, plus mass times velocity times distance for that stretch, added up. That only makes sense if the speed changes in jumps, staying constant along each stretch. But real motion does not do that. A falling body's speed changes continuously, at every instant, by an amount too small to name. Euler rewrote the action as an integral, mass times velocity, integrated along the path, which is the mathematical machinery for adding up infinitely many, infinitely small contributions. With that change, the action becomes a quantity you can compute for any motion whatsoever, not just for motion assembled out of uniform pieces. The second thing Euler did was find the missing conditions. Maupertuis' principle, stated the way Maupertuis stated it, is not true. It becomes true only if you add two requirements. The total energy of the system has to be conserved, and the total energy has to be the same for every trial path you are comparing against. Neither condition appears anywhere in Maupertuis' writing. He had not seen that they were needed, and if you drop them, the principle gives wrong answers. Euler found them, stated them, and in doing so, turned a slogan into something with a precise domain of validity. The third thing he did was demonstrate it working on a problem that mattered. He applied the principle to a body moving under a central attractive force, which is to say, a planet going around a star, and showed that the actual orbit is the one that makes the action stationary. To do that, he had to solve a genuinely new kind of problem, and it is worth pausing on why it was new. When you want the lowest point of a curve, you have one thing to vary. You slide a single number left and right and watch the height. That is ordinary calculus, and it had existed for 60 years. But when you want the path of least action, you are not varying a number. You are varying the entire shape of a curve, its height at every point along its length, simultaneously, and there are infinitely many such points. It is the same wall we ran into with the ramp. You are searching a space with infinitely many directions in it, and ordinary calculus has nothing to say about that. So Euler built a method. His approach was to approximate the curve as a chain of very many short, straight segments, then wiggle the position of one joint at a time, and demand that the action not change. Then take the limit as the segments become infinitely short and infinitely numerous. It works. It is also, by his own cheerful admission, laborious and inelegant, and reading it is hard work. Euler is a strange figure to encounter in the history of mathematics, because most of the great ones are difficult people, and he seems not to have been. He was generous with credit, to an extent that borders on the self-defeating. He almost certainly had the correct mathematical form of the action principle before Maupertuis published, in a more rigorous version, and he spent years insisting on Maupertuis' priority anyway. He wrote to be understood rather than to be admired, and his textbooks are still readable today by people who cannot read anything else from the 1700s. He went completely blind in 1771 and produced roughly half of his total output afterwards, dictating to assistants, apparently untroubled. But even Euler had not produced a general proof. He had a method, two conditions, and a worked example. The principle was still, strictly speaking, a conjecture that had never failed. The proof came from a 19-year-old. Joseph Louis Lagrange was born in Turin in 1736. He had intended to become a lawyer, like his family wanted, and he changed course after reading a paper by Edmond Halley about the use of algebra in optics. He taught himself mathematics almost entirely from books. By the age of 19, he was teaching at the Royal Artillery School in Turin, and he was working at the very front edge of the subject. In 1755, he wrote to Euler, describing a method he had developed for variational problems. It was not a refinement of Euler's chain of segments approach. It replaced it. Lagrange introduced a new symbol, the Greek letter delta, to represent an infinitesimal change not in a number, but in an entire function, the whole curve at once, and then built a formal algebra for manipulating it. Everything that had required geometric reasoning and limiting arguments became a matter of pushing symbols around according to fixed rules. Euler's response tells you a great deal about him. He wrote back that Lagrange had carried the theory to the highest summit of perfection, and that this had given him the greatest joy. Then he did something else. He had related results of his own, ready to publish. He held them back, deliberately, so that the unknown teenager in Turin could publish first and get the credit. Around 1760, roughly a year after Maupertuis died in Basel, still believing the idea had ruined him, Lagrange produced the general proof. The principle of least action stopped being a conjecture supported by examples. It became a theorem. Lagrange spent the next 30 years rebuilding the whole of mechanics on top of it, and published the result in Paris in 1788 under the title Analytical Mechanics. In the preface, he made a boast that has been quoted ever since. "One will not find figures in this work," he wrote. "The methods I expound require neither constructions nor geometrical or mechanical arguments, but only algebraic operations, subject to a regular and uniform course. No diagrams, not one, in a book about the motion of physical bodies." That sentence marks a change in what physics is. Newton's Principia is a geometry book. It argues with drawings, triangles, arcs, limiting constructions, figures you have to follow with your eye. Lagrange's Analytical Mechanics is an algebra book. After 1788, physics is increasingly something you write rather than something you draw, and the reason is that the action principle lets you write it. Hamilton, half a century later, described the book as a kind of scientific poem. Lagrange lived out the rest of his life in Paris, through the Revolution, and chaired the commission that built the metric system, which is why the units we have been using all evening exist in the form they do. He was protected from the laws expelling foreigners by the chemist Antoine Lavoisier, who intervened personally on his behalf. Lavoisier went to the guillotine in 1794, and Lagrange's remark afterwards has survived. "It took them only a moment to cut off that head, and 100 years may not produce another like it." So by the end of the 1700s, the situation is this. There is a quantity called the action. There is a rule saying that real motion makes it stationary. There is a rigorous mathematical machine for finding the path that does so. And there is a complete reconstruction of mechanics built on top of the whole thing. What there is not, anywhere, is an explanation of why any of it should be true. Lagrange proved that the principle gives the right answers. He did not, and could not, say why the universe has an action at all, or why it is the quantity it is. And before we can even get to that question, we have to do the thing itself. We have to actually search through an infinity of paths and pull one out. It is more straightforward than it sounds, and once you have seen it, you will not be able to unsee it in the rest of physics. We keep running into the same wall, so let us knock it down properly. The wall is this: how do you find the best member of an infinite family without checking the members? The answer comes from a place you already know, and I want to start there, because the trick is not to think about infinity at all. The trick is to think about a bowl. Imagine a smooth, round bowl, and imagine you are standing somewhere on the inside of it, on the slope. Now take a small step. If you step downhill, you drop. If you step uphill, you rise. Either way, the change in your height is roughly proportional to the size of your step. Step twice as far, drop twice as much. Now stand at the very bottom of the bowl and take the same small step. Something different happens. Whichever direction you step, you go up, but you go up by an almost absurdly small amount. Step a millimeter, and you rise by something like a millionth of a millimeter. The change is no longer proportional to your step. It is proportional to the square of your step, and squares of small numbers are savagely small. That is what being at the bottom means, operationally. Not that the height is low, but that the first-order response has vanished. Move a bit in any direction, and to first approximation, nothing happens. This is the entire reason that setting a derivative to zero finds a minimum. The derivative is the first-order response. Where it vanishes, the surface is flat, and where the surface is flat, you are at a stationary point. Now do exactly the same thing to a path. Suppose there is a true path, the one the system actually takes, and call it y. It runs from a fixed starting point to a fixed ending point. Now take that path and disturb it, not by moving one number, but by adding a small arbitrary wobble to the whole thing. Push it up a little here, down a little there, put a ripple in the middle, whatever you like. Call that wobble eta. The disturbed path is the true path plus eta. There is one restriction on the wobble, and it matters more than it looks. Eta has to be zero at both ends. Every trial path has to start where the true path starts and finish where the true path finishes, because otherwise you are not comparing routes between the same 2 points, you are comparing different journeys. So the wobble can do anything it likes in the middle, and it must vanish at the edges. Now compute the action of the disturbed path and subtract the action of the true path. If the true path really is the stationary one, then that difference has to vanish to first order in the wobble. Not exactly zero. There will generally be a leftover piece proportional to the square of the wobble, just like the bowl. But the piece proportional to the wobble itself must be gone. The reason is worth saying out loud, because it is the whole logic. Suppose that piece were not gone. Suppose the difference in action had a term proportional to eta. Then wobbling in one direction would increase the action, and wobbling in exactly the opposite direction, using minus eta instead of eta, would decrease it. And if you can decrease it, you were not at a stationary point to begin with. So the linear term has to die, for every possible wobble, or the path was not the one you were looking for. That is the principle, and it fits in a sentence. The action of any nearby trial path, minus the action of the true path, is zero to first order. That single statement is what physicists mean when they write, in the compressed notation of the subject, that the variation of the action is zero. Delta S equals 0. 3 symbols. Everything in this video is inside them. Now we need to deal with something I have been quietly postponing, which is the question of what the action actually is in its modern form, because the thing Maupertuis wrote down is not the thing in your physics textbook. The path from one to the other is short, and it is worth walking because the destination is genuinely peculiar. Start with Euler's version of Maupertuis' action, mass times velocity, integrated along the path, over distance. Velocity is distance divided by time, so a small element of distance is velocity multiplied by a small element of time. Substitute that in, and the action becomes mass times velocity squared, integrated over time. But mass times velocity squared is exactly twice the kinetic energy. So the action is twice the kinetic energy, integrated over time. That is already a simplification. The action is no longer about distance at all. It is about kinetic energy accumulating as the clock runs. Now bring in Euler's condition that total energy is conserved. Total energy is kinetic plus potential. So kinetic energy equals total energy minus potential energy. Take one of the two copies of kinetic energy and rewrite it that way, and the action becomes the integral, over time, of kinetic energy plus total energy minus potential energy. The total energy term is a constant, so integrating it over time just gives the energy multiplied by the elapsed time, and now watch it disappear. When you take the variation, when you compare nearby paths, that term contributes a piece involving the change in energy between paths, which is zero, because Euler's second condition says all the trial paths have the same energy, and it contributes a second piece involving the change in elapsed time between paths. So if you also restrict yourself to comparing paths that take the same amount of time, that piece dies too. What is left standing, after all of that, is this. The variation of kinetic energy minus potential energy, integrated over time, is zero. Kinetic minus potential. I want you to sit with how odd that is. Kinetic plus potential is the total energy, one of the most important quantities in all of physics. Conserved, meaningful, physically interpretable. Kinetic minus potential is not anything. It is not conserved. It has no name in ordinary language. You cannot point at it. There is no experiment that measures it directly. It is the difference between two energies for no reason anybody can articulate. And it is the most important quantity in physics. It is called the Lagrangian, written with a capital L, named for the man who did not invent it. The integral of the Lagrangian over time is the action, written S. And the principle of the whole of physics is the statement that the variation of S is zero. The first person to write it in this form was William Rowan Hamilton, in a pair of papers published in 1834 and 1835, under the title On a General Method in Dynamics. Hamilton was Irish, and he was a prodigy of the sort that makes other prodigies uncomfortable. Appointed Royal Astronomer of Ireland and Professor at Trinity College Dublin, while still an undergraduate, at 22. He is more famous now for quaternions, which he invented in a flash of insight while walking along the Royal Canal in Dublin on the 16th of October 1843, and immediately carved into the stone of Broome Bridge. The work on dynamics is by a wide margin the more consequential of the two. His version is called Hamilton's principle, and it differs from Maupertuis' version in ways that turn out to matter enormously later. In Maupertuis' form, the trial paths all have to have the same energy, but they can take different amounts of time, and what the principle gives you back is the shape of the track through space. In Hamilton's form, the trial paths all have to take the same amount of time, but can have different energies, and what you get back is the complete motion, where the object is at every instant, not merely what curve it follows. Hamilton's version needs a start point, an end point, a start time, and an end time. Maupertuis needs only the 2 points. And Hamilton's version is the one that generalizes to fields, to relativity, to quantum mechanics, which is why it is the one that survived, and why the modern statement of the deepest principle in physics is named after a man who arrived a century after the idea and roughly 50 years after the proof. Let me stop and put the pieces on the table, because we have covered a lot of ground, and this is the point where they lock together. We started with a bead on a ramp and a question about shape. That question forced the invention of a way to search through infinitely many curves at once. Applied to light, that same search turned Snell's law from a brute fact into a consequence of minimizing time. Applied to matter, it produced a quantity called the action. Made rigorous by Euler, proved general by Lagrange, and rewritten by Hamilton, it became a single condition: the action is stationary, from which the motion of anything can be extracted. What we have not done yet is watch it produce something we recognize. So far, it is a beautiful machine with nothing coming out of the far end. That changes now with the simplest experiment I can think of. I am going to throw a ball straight up in the air. I am holding a ball. I throw it straight up, and a second later I catch it in the same hand. That is the entire experiment. There is nothing simpler in physics. The ball leaves my hand at a known height at a known moment, and it arrives back at a known height at a known moment, and in between it does something that every human being has watched 10,000 times without ever once wondering whether it needed explaining. We are going to explain it from the principle of stationary action, and we are going to do it slowly, because this is the moment where the machine produces something you already know, and I want you to see it arrive. Let the height of the ball be described by some function of time. Call it y. At the start of the second, y has one value. At the end, y has another. Between those two fixed endpoints, we are going to consider every conceivable way the ball could get from one to the other. Picture them. There is the real arc. Up, slowing, hanging, falling, back down. There is one where the ball rockets up to the ceiling and plummets back. There is one where it barely leaves my hand and hovers around at that height for most of the second before scurrying back. There is one that wiggles up and down 4 times on the way. There is one with a sharp kink in it. Every single one of these is a valid trial path, and there are infinitely many of them. The only requirement is that they all start where the real one starts, end where the real one ends, and take exactly 1 second. Now, for each of these imaginary journeys, compute the action. To do that, at every instant along the path, take the kinetic energy of the ball and subtract its potential energy. Kinetic energy is 1/2 the mass times the speed squared, where the speed is how fast the height is changing at that instant. Potential energy is the mass times the strength of gravity times the height. Subtract the second from the first. That is the Lagrangian at that instant. Now add up the Lagrangian over the whole second, integrate it over time, and you have one number, the action, attached to that entire path. Every trial path gets a number, the real one gets a number too, and the claim is that the real path is the one where that number is stationary. Here is how you find it. Write the trial path as the true path plus a wobble. The wobble is 0 at both ends, as always. Now compute the action of the trial path. When you expand it out, the kinetic energy term contains the rate of change of the true path plus the rate of change of the wobble, squared. Squaring that gives you 3 pieces: the true one squared, a cross term with 1 factor of each, and the wobble squared. The potential energy term contains the true height plus the wobble. Now subtract the action of the true path. Everything that involves only the true path cancels exactly. It appears in both, and it goes. The wobble squared piece is second order, and we agreed to ignore those. What survives is the first order remainder, and it has exactly 2 terms in it. The first term is the mass times the velocity of the true path times the rate of change of the wobble. The second is the wobble times the rate of change of the potential energy, with height, with a minus sign. And this whole thing has to vanish. There is one problem. We want to factor the wobble out of both terms so that we can use its arbitrariness against it. But the first term does not contain the wobble, it contains the rate of change of the wobble. Those are not the same thing. The fix is a standard piece of calculus called integration by parts, and all it does is move a derivative from one factor onto the other. Apply it, and the rate of change of the wobble gets traded for the rate of change of the velocity, which is the acceleration, and the wobble itself is left standing free. Integration by parts always leaves behind an extra piece evaluated at the two endpoints, and that piece contains the wobble evaluated at the endpoints, which is 0. It was always going to be 0, because we insisted from the beginning that the wobble vanish at both ends. That condition, which looked like a technicality when we set it up, is what makes the entire derivation work. So now everything is multiplied by the wobble, and the whole integral must equal 0. And here is the step that does the real work. The wobble was arbitrary. It could have been a bump near the start, or near the end, or a narrow spike anywhere at all. If the integral of the wobble times some quantity is 0 for every conceivable wobble, then that quantity has to be 0 everywhere along the path. Because if it were not 0 somewhere, you could simply choose a wobble that was a little bump sitting exactly there, and the integral would not vanish. This is called the fundamental lemma of the calculus of variations, and it is the hinge the whole subject turns on. So the quantity multiplying the wobble is 0. And what is that quantity? It is the mass times the acceleration of the ball plus the rate at which the potential energy changes with height. Now translate both halves into English. The rate at which potential energy changes with height, with a minus sign in front of it, is the force. That is not a coincidence or a definition invented for this purpose. It is what a force is in energy language. If moving in some direction lowers your potential energy steeply, there is a strong force pulling you that way. Gravity is what it is, because being higher costs energy. And the second derivative of position with respect to time is the acceleration. That is just what acceleration means. So the equation the machine has produced, when you read it back, says mass times acceleration equals force. F equals ma. Newton's second law came out of the bottom of that derivation. We did not put it in. Nowhere in the setup did we mention forces, or Newton, or anything about pushing and pulling. We wrote down two energies, subtracted them, integrated, and demanded that the result be flat, and out came the most famous equation in classical physics, like a remainder falling out of a long division. Let me say the thing I planted at the very beginning again, because it means something different now. For any motion you care to describe, there is a number attached to the whole journey, and the journey that actually happens is the one where that number stops changing. You now know what the number is. It is the accumulated difference between kinetic and potential energy, and you have watched Newton's law come out of it. The same derivation, done without committing to a ball or to gravity, produces a general result. It is called the Euler-Lagrange equation, and it says that the rate of change over time of how the Lagrangian responds to velocity minus how the Lagrangian responds to position equals 0. One such equation for each coordinate you are using. Feed it a Lagrangian, turn the handle, and out comes the equation of motion for whatever system that Lagrangian describes. It does not care what the system is. And notice what has quietly happened to Fermat along the way. His principle of least time was never a separate law belonging to optics. It is this same principle applied to light. Two rules that looked like they came from different subjects, one about beams and mirrors, one about falling bodies, have collapsed into a single statement. That is the first time in this story that the action does the thing it is going to keep doing for the rest of the night. Absorb an entire field of physics and make it a special case. I want to be careful about how much weight I put on this, because it is easy to overstate, and it does not need overstating. Nobody is claiming Newton was wrong. The two statements are mathematically equivalent. Each can be derived from the other, and they make identical predictions about every measurable thing in the world. But equivalent is not the same as equally fundamental. And here is the uncomfortable part. Most people carry F equals ma around as bedrock. It is the one equation almost everyone remembers from school. It sits underneath everything else in the mental picture, the floor of physics, the thing that does not need explaining because it is what everything else is explained in terms of. It is not the floor. It is a consequence. The fall of a dropped phone, the arc of a thrown ball, the weight of your own body pressing into whatever you are lying on right now. All of it obeys F equals ma, and F equals ma is downstream of something else, something with no everyday name, something that is not energy, not force, not momentum, not anything you could point at or measure directly, and which nobody in this entire story has been able to explain the meaning of. Kinetic minus potential, integrated over time, made flat. That is what is holding you down. And having watched this machine reproduce Newton, the natural reaction is the one every physics student has. This is enormously more complicated than just writing F equals ma in the first place. Why would anyone ever bother? There is an answer to that, and it is a very good one, and it comes with a correction to something I have been letting slide since the beginning. The objection is fair. We just did all of that to arrive at an equation we already had. If the two descriptions are equivalent, and one of them is a single line you can write from memory, why would anybody choose the other one? The answer is that in practice, the action method is enormously easier, and the reason is one word: vectors. A force is a vector. It has a size and a direction, and to use it you must resolve it into components, keep the signs straight, and account for every single force acting on the system. That last part is where people come to grief, because a great many of the forces in a real problem are ones you do not care about and cannot easily calculate. The tension in a string, the normal force from a track pushing back on a bead, the reaction at a hinge. These are constraint forces. They exist purely to stop the system doing something it cannot do. And to use Newton's method, you have to solve for them, even though the answer is of no interest whatsoever. Energy is not a vector. Energy is a single number. Kinetic energy has no direction. Potential energy has no direction. To build a Lagrangian, you write down one number, write down another number, subtract, and turn the handle. There are no components to resolve, and no signs to get backwards. And the constraints handle themselves. If a bead is threaded on a wire, it has exactly one way to move, so you describe it with exactly one coordinate, how far along the wire it has got. And the wire's grip on the bead never appears in the calculation at all. It cannot appear, because you never gave the bead a way to leave the wire in the first place. In Newton's language, you have to work out the force the wire exerts, and then show that it exactly cancels the component of motion you do not want. In Lagrange's language, you simply do not mention it. Then there is the freedom of coordinates, which is the part that working physicists actually love. Write your energies in whatever coordinates suit the problem. Ordinary left, right, up, down coordinates, if that is convenient. Angles and radii, if the thing is going in circles. Rotating coordinates that spin with the apparatus. Some strange pair of angles that only make sense for this one machine. It does not matter. The Euler-Lagrange equation delivers the correct equations of motion in whatever coordinates you handed it, automatically, with no extra work. Doing that same transformation by hand, with vectors, is famously error-prone, and the errors are of the silent kind that give you plausible wrong answers. The standard demonstration is a double pendulum. Hang a pendulum from a fixed point, then hang a second pendulum from the end of the first one. Trying to write F equals ma for that is genuinely unpleasant. The second pendulum's pivot is not a fixed point. It is swinging around, accelerating, changing direction constantly. So the second bob is living in a frame of reference that is itself accelerating, which means fictitious forces appear, and you have to track all of them correctly while everything is moving. Writing the energies takes a few lines. The kinetic energy of the first bob in terms of its angle. The kinetic energy of the second bob in terms of both angles, since its position depends on where the first one is. The potential energies from the two heights. Subtract. Apply the Euler-Lagrange equation, once for each angle, and you have the complete equations of motion for one of the most chaotic systems in classical mechanics. That is not an academic point. It is how the simulations are actually built, in physics software, in engineering packages, in the code that plans spacecraft trajectories and models robot arms and animates physical motion in films and games. Nobody writes vector force balances for complicated systems anymore. They write a Lagrangian. And if you do happen to want the constraint forces, if you are an engineer who needs to know whether the hinge will actually hold, the method hands them back to you on request. You add the constraint into the calculation with an extra unknown multiplied by it, a device Lagrange invented for the purpose. When you solve, that extra unknown turns out to be exactly the constraint force, so the information was never lost. It was simply not in your way unless you asked for it. Structural engineers use this every day without necessarily knowing whose idea it was. The way it was once put to me is that with vectors, you have to be a good physicist to get the right answer, and people who are good at mechanics can do it. With the Lagrangian, you have to be a careful bookkeeper. It moved physics from a craft into a procedure, and that is why it took over. Now the correction I owe you. I have been saying least action all evening, because that is what everyone in this story called it, and that is what most people call it today. It is wrong, and the way in which it is wrong matters a great deal for what comes next. Go back to the bowl. When you set a derivative to 0, you are not guaranteed to have found the bottom of a bowl. You might be at the top of a hill, where the surface is also flat, and where any step takes you down. Or you might be at a saddle, the shape of a mountain pass, or a horse's saddle, or a Pringle, where the surface curves up in one direction and down in another, and is flat at the center. Setting a derivative to 0 finds a flat spot. It does not tell you what kind. The variational condition has exactly the same weakness, and it is not a theoretical worry. For short journeys, the true path usually is a genuine minimum of the action. For longer ones, it very often is not. The cleanest example is the simplest oscillating system in physics, a mass on a spring. If you look at a stretch of its motion lasting longer than half a full swing, the real trajectory is not a minimum of the action at all. It is a saddle point, and you can construct nearby paths whose action is smaller. The mass does not take them. The principle still works perfectly. It just is not minimizing anything. There is even a case where the true path is a maximum, and it is one of the most famous results in all of physics. But that one belongs a little further on, so I will leave it sitting there. Mathematicians have since made this precise. There is an entire field, called Morse theory, devoted to classifying the flat spots of quantities like the action, and counting how many independent directions you could move in to make the action smaller. That count has a name, the index, and for a mass on a spring, it goes up by 1 every half swing, forever. The longer the journey you consider, the further the real path is from being a minimum. It is not a marginal failure at the edges. It gets worse the longer you look. The correct name for the rule is the principle of stationary action. None of the mathematics changes. Every prediction stays exactly where it was. What changes is the story you tell yourself about what the universe is doing, and that story has been quietly wrong for 280 years. Because the word least smuggles in a meaning. Least implies economy. It implies thrift, efficiency, a resource being conserved, a preference being exercised. It is why Maupertuis reached for the phrase, the true expense of nature, and it is why the principle has been used as an argument for cosmic design ever since. If nature is minimizing, then nature is choosing, and if nature is choosing, something is doing the choosing. But nature is not minimizing. Nature is sitting at a point where the action happens to be flat, and flat includes hilltops and saddles and mountain passes. There is no economy in a saddle point. Nothing is being conserved. Nothing is being spent carefully. Nature is not being economical. Nature is standing still. Hold on to that sentence. It is going to come back twice more tonight, and the second time it comes back it will stop being a correction about vocabulary and start being the actual mechanism. But before we can get there, I have to show you how far this thing reaches, because so far we have only used it on beads and balls and pendulums. That is not what it is for. What it is for is considerably larger, and it is the reason the title of tonight's video says what it says. Everything we have done so far has been mechanics. Beads, balls, pendulums, planets. That is where the principle was born, and it is where it was proved, and if that were the end of the story, it would be an elegant reformulation of one branch of physics, and nothing more. It is not the end of the story, it is the beginning of the only story physics has. Start with electricity and magnetism. In the 1860s, James Clerk Maxwell assembled the behavior of electric and magnetic fields into a set of equations that describe every electrical phenomenon there is: currents, magnets, radio, light, the charge moving through the device you may be listening to this on. 4 equations, historically arrived at by gathering up decades of experimental results from Faraday and Ampere and Gauss, and stitching them into a consistent whole. All 4 of them come out of a single Lagrangian. You write down one expression built from the electromagnetic field, add one term describing how the field couples to electric charge, and demand that the action be stationary. Maxwell's equations drop out, the same way F equals ma dropped out of the ball. And then something much stranger happens, which is that you can run the logic backwards. Suppose you know nothing about electromagnetism at all. Suppose you only have the action describing electrons, and you notice that this action has a certain symmetry. You can change a particular abstract property of the electron field differently at every point in space, and demand that the physics not notice. Make that demand, and the mathematics refuses to comply unless you introduce a new field to compensate. That new field is the electromagnetic field. The photon is not put in by hand. It is forced into existence by insisting that the action stay unchanged under a symmetry. Light exists because of a requirement on an action. That approach has a name, the gauge principle, and it was developed by Hermann Weyl and then by Yang and Mills in 1954, and it is the single most productive idea in 20th century theoretical physics. Every fundamental force we know about is now understood this way. You do not discover forces, you discover symmetries, and the forces are what the action has to grow in order to respect them. Now relativity. The action for a free particle moving at relativistic speeds is startlingly simple. It is proportional to the proper time along the path, the time measured by a clock riding along with the particle, with a minus sign in front. Making the action stationary therefore means making the proper time as large as it can be. That is the twin paradox, restated as a variational principle. Take 2 twins, one who stays put and one who travels out at high speed and returns. The one who stayed still is older when they meet. And the reason, in this language, is that the straight world line through space-time is the one with the most proper time on it. The travelling twin took a bent path and spent less of her own time getting there. Notice what that means for the vocabulary problem. Here the stationary value is a maximum. Nature is not economizing. It is doing the opposite, if you insist on reading it that way. This is the case I mentioned earlier and left sitting, and it is about as clean a demonstration as you could ask for. That least was never the right word. Now gravity. In general relativity, gravity is not a force. It is the geometry of space-time, curved by whatever is in it. And the equations that govern that curvature, the Einstein field equations, 10 coupled equations of appalling complexity, come from an action too. It is called the Einstein-Hilbert action, and it is, in words, the total curvature of spacetime added up over all of spacetime, with a constant in front. David Hilbert derived the field equations that way. He wrote down the simplest possible action a curved spacetime could have, made it stationary, and got the equations out. He presented the result in Göttingen on the 20th of November, 1915, 5 days before Einstein presented his own version in Berlin, having reached the same place by an entirely different road. Einstein had spent 8 years fighting his way there through physical reasoning. Hilbert asked what the simplest action would be. Sit with that for a second. The curvature of space and time around a star, the bending of light past the sun, the slowing of clocks near a mass, the existence of black holes, the expansion of the universe, all of it follows from making one integral stationary. And then, particle physics. The entire content of the Standard Model. Every quark, every lepton, the strong force, the weak force, electromagnetism, the Higgs field that gives particles their mass, every interaction between all of them is one Lagrangian, not a set of laws, one expression. It is short enough to print on a coffee mug, and the gift shop at CERN sells it on mugs and t-shirts precisely because that is a startling thing to be able to do. Physicists buy them. The joke, which is not really a joke, is that you can carry the fundamental laws of matter around in one hand while you drink your coffee. The Feynman diagrams you may have seen, the little stick figures of particles colliding and scattering, are not pictures of events. They are a graphical bookkeeping scheme for evaluating terms in the expansion of that action. Every diagram is a term. The pictures exist to keep track of the arithmetic. And then there is a theorem, which I will mention briefly because it deserves a video of its own rather than a paragraph in this one. It was proved in Göttingen and published in 1918, and it says that every continuous symmetry of the action corresponds to a conserved quantity. If the action does not care when you start the experiment, energy is conserved. If it does not care where you set it up, momentum is conserved. If it does not care which way it is facing, angular momentum is conserved. The great conservation laws of physics are not separate postulates at all. They are consequences of what the action does not depend on, which means the deep structure of physics does not live in forces. It lives in the action. There is one more consequence of all this, that changes how the subject is practiced, and it is worth stating plainly, because it is not something that gets said outside of graduate seminars. Since roughly the 1950s, nobody in fundamental physics discovers forces. That is not how the work is done anymore. What a theoretical physicist actually does is this: decide what symmetries the world ought to respect, write down the most general action consistent with those symmetries and with a small number of technical conditions, and then let the mathematics generate the dynamics. The predictions come out the far end and get compared to experiment. If they fail, you change the action and try again. That is the method. Every theory in modern physics was built that way. It is astonishingly effective, and it has one glaring feature that we will come back to at the end of tonight, which is that the method tells you exactly what to do with an action and tells you absolutely nothing about where the action comes from. Let me collect this, because the size of it is easy to lose sight of when the examples come one after another. Classical mechanics, an action. Optics, an action. Electricity and magnetism, an action. Special relativity, an action. general relativity, an action. Quantum field theory, and every particle we have ever detected, an action. Conservation of energy, momentum and angular momentum, consequences of the symmetries of an action. Even string theory, which may or may not describe anything real, is built on an action. In its simplest form, the area of the surface a string sweeps out through space-time, made stationary, which is mathematically the same condition a soap film obeys when it stretches between two wire loops in your kitchen sink. Every branch of physics, every scale, from below the proton to the size of the observable universe, all of it, written in the same one line, the variation of the action is zero. There is a phrase from earlier in tonight that I want to bring back, because it fits here better than it fitted where it started. When Johann Bernoulli read an unsigned solution and recognized Newton, he said, "As the lion is known by its claw." He meant that a single piece of work can carry a signature so distinctive that you do not need a name attached to it. That is what physics has found. Look at mechanics, at light, at electromagnetism, at gravity, at the interior of the proton. Completely different phenomena, discovered by different people in different centuries with different instruments. And every single one of them, when you get to the bottom of it, is written in the same hand, the same structure, the same one line. You could identify it from any one of them without being told. The claw is unmistakable, and there is no lion. Nobody can tell you what the action is, why it exists, or why the universe should be organized around making one quantity flat. We are still not ready to answer the question we started with, but there is a clue, and it had been sitting in plain sight for 40 years before anybody read it correctly, hiding, of all places, inside the problem of why fires do not kill everyone who lights one. At the very end of the 1800s, classical physics had a problem that it could not talk its way out of, and the problem was fire. Heat something up and it glows. A poker in a hearth goes from black to dull red to orange to yellow-white as it gets hotter. That progression is regular. It is the same for every material. And by the 1890s, it had been measured to high precision. Physicists had the curve. What they did not have was a theory that produced it. When you apply the physics of the day to a hot object radiating light, the answer you get is not merely wrong. It runs away. The theory says that the object should pour out more and more energy at shorter and shorter wavelengths, without limit, forever. The total energy, radiated by anything warm, comes out infinite. That result is called the ultraviolet catastrophe, and the name is not hyperbole. If the calculation were right, opening an oven door would sterilize the room. Every candle would be lethal. The fact that you can sit near a fire and be comfortable is, according to classical physics, impossible. Max Planck spent years on it and eventually did something he described as an act of desperation. He assumed that energy could not be emitted and absorbed in arbitrary amounts. It came in packets. A packet of light at a given frequency carried a fixed amount of energy, proportional to that frequency, and nothing smaller was allowed. That assumption fixed everything. The runaway disappears, because producing very short wavelength light requires very large packets, and a warm object simply does not have enough energy in one place to make them. The predicted curve matched the measured one exactly. It was the first crack in classical physics and the beginning of the whole quantum enterprise, and Planck himself did not believe it meant anything physical for years afterwards. It is worth knowing how reluctantly he did it. Planck was 52, deeply conservative in his physics, and he had spent the better part of a decade trying to derive the radiation curve from thermodynamics, without assuming anything new. He described the weeks that followed as the most strenuous work of his life, and he described the packet assumption as an act of desperation, something he was willing to do because, in his words, A theoretical interpretation had to be found at any price. He presented it in Berlin in December of 1900. Then he spent the next decade trying to get rid of it, attempting again and again to recover the same curve without quantization, and failing every time. 5 years later, Albert Einstein took the packets seriously in a way Planck had not. He argued that light itself is made of them, not merely emitted in them, and used that to explain the photoelectric effect, why shining light on a metal knocks electrons out of it only above a certain color, no matter how bright the light is. That is the work he was eventually given the Nobel Prize for, not relativity. The packets were real. The constant of proportionality, the number connecting a frequency to the size of its packet, is now called Planck's constant. It is written h, and Planck gave it a name in German, in his own papers, that almost nobody quotes. He called it the Wirkungsquantum, the quantum of action. That word is not decoration, and it is not a loose translation. Look at the units. Planck's constant is an energy divided by a frequency. A frequency is a number of cycles per second, so dividing by it multiplies by seconds. So Planck's constant is measured in joule seconds, energy multiplied by time. Now go back to a half-kilogram ball rolling 6 meters at 3 meters a second. We computed the action for that, 9 units, and I asked you to hold on to what the units were. Kilogram meters squared per second. Work it through, and those are the same units. Mass times velocity times distance is mass times distance squared over time. Energy times time is mass times distance squared over time squared times time, which is mass times distance squared over time. Identical. Planck's constant is measured in units of action. Exactly the quantity Maupertuis invented in 1744 and was ridiculed for. The quantity that has no everyday meaning and no direct measurement. The difference between two energies accumulated over time. The fundamental constant of the quantum world, the number that determines where reality stops behaving classically and starts behaving strangely, is a quantity of action, not an energy, not a force, not a length or a mass or a speed. Nature's smallest indivisible unit, the grain size of reality, is a unit of the one quantity nobody can interpret. It is worth being precise about the value, because the precision is part of the story. Planck's constant is 6.62607015 times 10 to the minus 34 joule seconds. That number is not measured. Since the redefinition of the International System of Units in 2019, it is defined, fixed by decree at that exact value, and the kilogram is now defined in terms of it. The standard unit of mass, which for 130 years was a lump of platinum and iridium in a vault outside Paris, is now derived from a quantity of action. The version physicists actually use in equations is Planck's constant divided by 2 pi, written h bar, and it comes to about 1.05 times 10 to the minus 34 joule seconds. Hold that number. Everything in the next part depends on how small it is. And the clue kept surfacing when Niels Bohr built the first workable model of the atom in 1913, and when Arnold Sommerfeld extended it. The rule they used to decide which electron orbits were allowed was not a rule about energy or radius. It was a rule about action. Take the momentum of the electron, follow it once around its orbit, add up momentum times distance all the way around, which is precisely Maupertuis' quantity, and the answer must be a whole number multiplied by Planck's constant. Read that again. The rule that produced the spectrum of hydrogen, the first genuine success of quantum theory, was a rule saying that action comes in whole numbers. And it goes further than the hydrogen atom. Wherever quantum mechanics has a natural scale, it is a scale of action. The uncertainty principle, which says you cannot pin down a particle's position and its momentum at the same time, is not a statement about energies or distances on their own. It says that the uncertainty in position, multiplied by the uncertainty in momentum, cannot be smaller than a certain amount, and position times momentum is, once again, action. The limit on how precisely you can know the world is expressed as a minimum quantity of action. Nature appears to have a grain size, and the grain is made of the stuff Maupertuis guessed at, while trying to work out why light bends. There is a way of picturing this that helps. Imagine the space of all possible states of a system, every combination of where something is and how fast it is going, laid out as a surface. Classically, that surface is smooth, and a system can sit anywhere on it, at any point, with infinite precision. Quantum mechanically, it is not smooth. It is tiled into cells, and each cell has the same fixed area, and that area is Planck's constant. You cannot specify a state more finely than one tile, and the area of a tile, being position times momentum, is an action. For about 40 years, this sat in the middle of physics without an explanation. Everyone could see that action kept appearing wherever the quantum world touched the classical one. Nobody could say why. There was a classical principle involving a quantity called the action, which produced all of physics for no known reason, and there was a quantum constant measured in units of that same quantity for no known reason, and nobody could join them. The joining, when it came, was performed by a physicist who was still a graduate student, working from a single sentence in an obscure paper that almost nobody had read, after a conversation at a beer party. And what he found is the closest thing anyone has ever produced to an answer to tonight's question. It explains, completely and beautifully, why the principle of stationary action is true. It explains why we see one path instead of many. It dissolves the entire uncomfortable business of the universe, appearing to know where things are going before they get there. It also does something that people rarely mention when they tell this story. It takes the mystery and moves it down one floor, where it is still sitting. We are still not ready to answer the question we started with, but we are one step away. In 1933, Paul Dirac published a short paper in a Soviet journal called the Physical Journal of the Soviet Union. Its title was The Lagrangian in Quantum Mechanics. It ran to about 8 pages, and almost nobody read it, partly because of where it appeared, and partly because nobody could see what to do with it. In it, Dirac noticed something curious. If you ask, in quantum mechanics, for the quantity that describes a particle getting from one place to another over a very short interval of time, and if you compare it to the classical action for that same short interval, the two are related. Specifically, the quantum quantity corresponds to an exponential, a rotation through an angle, where the angle is the classical action for that interval divided by h bar, corresponds to. That was the phrase Dirac used. He did not say equals. He did not say is proportional to. He wrote corresponds to, published it, and moved on to other things. Let me put you in Princeton in the spring of 1941. There is a beer party at the Nassau Tavern, on the main street, a short walk from the university. Richard Feynman is 23 years old and is a graduate student working under John Wheeler. He has been chewing on a problem for months, and at some point in the evening he says it out loud. He wants to build quantum mechanics, starting from the Lagrangian rather than from the energy, and he cannot find a way in. A visiting physicist named Herbert Yale, a European who has arrived in Princeton by way of an internment camp in France, hears him. Yale says there is a paper, Dirac, a few years back. It does exactly that. The next morning they are in the Princeton library with the bound volume open on a table, and Feynman is reading the sentence with the phrase corresponds to in it. He asks Yale what it means. Yale does not know. He assumes Dirac meant something loose, an analogy, a family resemblance. Feynman goes to the blackboard. He takes the phrase and refuses the looseness. He assumes Dirac meant something exact, that the quantum quantity is proportional to that rotation, with an actual constant of proportionality. He works out what follows for a short time interval, then for the next one, then for a chain of them. Euler stands behind him, copying it into a notebook. Within the hour, out of the bottom of the blackboard, the Schrödinger equation appears, the central equation of quantum mechanics, which had been derived in a completely different way 15 years earlier. Euler, watching, says something that Feynman quoted for the rest of his life. He says that Americans are always trying to find out how something can be used. Feynman built the full framework into his Princeton doctoral thesis in 1942, under a title that could be the title of this video, The Principle of Least Action in Quantum Mechanics. The complete formulation was published in April of 1948 in Reviews of Modern Physics, Volume 20, pages 367 to 387, as Space-Time Approach to Non-Relativistic Quantum Mechanics. Here is the picture it produced, and it is the strangest thing in this entire story. A quantum particle going from one place to another does not take a path, it takes every path. Not metaphorically, every path. The straight one, the curved one, the one that loops backwards, the one that wanders out past the orbit of the moon and comes back inside a millionth of a second, the one that zigzags 1,000 times. Every conceivable route through space, including all the absurd ones, is included, and each of them contributes. What each path contributes is not an amount, it is a direction. Picture a little arrow attached to each path, all of them the same length, but pointing different ways. The direction the arrow points is set by the action of that particular path, divided by h bar. That is the angle. Large action means a large angle of rotation, and you find out what the particle does by taking all the arrows and adding them nose to tail from every path there is and looking at what you end up with. Now watch what happens when you do that, because this is where 280 years of mystery resolves itself. Take some wild path, the one that loops behind your head. Now take a path just slightly different from it, barely distinguishable, a hair's width away. Because the wild path is nowhere near stationary, that tiny change in the route produces a real change in the action. Divide that change by h bar, which is a number around 10 to the minus 34, and the angle change is enormous. The two arrows, from two nearly identical paths, point in completely different directions. So all the wild paths come with arrows pointing every which way, in complete disorder. Add them nose to tail, and you go nowhere. They cancel. Not approximately, utterly. Now take the path where the action is stationary. Stationary means, precisely, that wobbling the path does not change the action to first order. That is the definition we built in the middle of tonight. So take that path, and a neighbor a hair's width away, and their actions are almost exactly the same, which means their arrows point almost exactly the same way. Every path in that neighborhood contributes an arrow lined up with all the others. Add them nose to tail, and they do not cancel. They stack. They build into something long. Everything cancels, except the neighborhood of the path where the action is stationary. That is what is left over. That is the path you see. That is why the principle is true. Let me put you inside it, because I think you should feel this one rather than follow it. You are watching a ball leave a hand. Do not watch the arc. Watch all of them. Every possible route the ball could take between leaving and landing is happening at once, laid over each other, filling the room and the building and the space beyond it. The ball going straight up, the ball going through the ceiling, the ball taking a long, slow loop out past the window and returning, the ball trembling through 10,000 tiny zigzags on its way across. Each one carries a small arrow, spinning. Out among the wild roots, the arrows are pointing in every direction there is, and they sum to nothing at all. They erase each other so completely that those paths might as well never have occurred. But close in, hugging the one smooth arc, the arrows come into alignment, one after another, all facing the same way, adding. The arc you actually see is not a route the ball chose. It is the residue. It is the small band of paths that failed to cancel. And nothing decided anything. Nothing calculated a total. Nothing compared alternatives. There is no optimizer anywhere in the machinery. There is only every possibility happening, and almost all of it destroying itself. And what survives that destruction is the thing we call reality. Nature is not being economical. Nature is standing still. That sentence started as a pedantic correction about vocabulary. It is now the mechanism. There is no economy because there is no choosing. There is a place where the action is flat, and flatness is exactly the condition under which neighboring contributions agree with each other instead of cancelling. The universe is not thrifty. It is interfering with itself, and stationary is where the interference is constructive. Now the scale, because the numbers here are what make the classical world classical. Take a tennis ball thrown across a room. Work out its action for that journey, and you get something on the order of a joule second. Divide by h bar. The phase angle comes out around 10 to the 34th. That is not 34 radians. It is a 1, followed by 34 zeros. The arrow has spun around something like 100 million times. Now, shift the ball's path by an amount too small for any instrument to detect, and that phase changes by billions of full turns. The cancellation among non-stationary paths for an object that size is not merely strong. It is absolute, to a precision no measurement will ever approach. Which is why a ball has a trajectory, and you can catch it. For an electron, the action along a typical path is comparable to h bar. The arrow barely turns at all as you vary the path. The cancellation is feeble. Wide families of paths survive, and they interfere with each other visibly, and the electron does not have a trajectory. It has an interference pattern. That is the whole of the difference between the world you can catch things in and the world underneath it, and the difference is a ratio. There is a version of this you can watch on a table. Cut 2 narrow slits in a card and shine light through them onto a wall, and you get stripes, bright bands and dark bands where you would expect 2 bright lines. In the sum over paths picture, the card has removed almost every route from the calculation and left only 2 families of paths, one through each slit. Their arrows arrive at the wall, having turned by different amounts, because the 2 routes are different lengths. Where the arrows arrive aligned, they add and you get brightness. Where they arrive opposed, they cancel and you get darkness. Widen the analysis to include every path through a single slit, and the softer, more complicated single slit pattern falls out of the same arithmetic. The stripes on the wall are the cancellation, made large enough to see. And this is not a picture invented to make people feel better about quantum mechanics. It is a working tool. The masses of the proton and the neutron are computed from first principles by taking the path integral for the strong nuclear force, chopping space-time into a lattice of points, and having a supercomputer numerically add up the contributions of the field configurations. The proton mass comes out right to about 1%. Almost none of the mass of your body comes from the Higgs field, incidentally. The overwhelming majority of it is the energy of the strong force churning inside your protons and neutrons, and that number is obtained by summing over histories. It was not adopted quickly. For years after 1948, Feynman's formulation was regarded as an eccentric restatement of things already known, useful for intuition and not much else. It is now the standard language of quantum field theory, the framework the standard model is actually written in, and the basis of most of the calculations that get compared to data at particle accelerators. The eccentric restatement became the way the subject is done. This also, incidentally, closes the loop on Fermat. Light does not take the fastest path. Light takes every path, and every path except the neighborhood of the stationary time one cancels out. That means Fermat's result, from 1662, was a quantum mechanical result. He was 3 centuries early and did not know what he was looking at. And the teleology problem, the one that has been sitting under this whole video, the discomfort about the particle needing to know its destination before setting off, evaporates. The particle does not know anything. It does not select. It is not looking ahead. Everything happens, and cancellation does the rest. Which sounds like an ending. It is not one. Because if you look carefully at what we just assumed in order to get here, there is something sitting in the middle of it that nobody has ever explained, and the mystery has not been solved. It has been moved. We have arrived at the question we started with, and I am going to answer it properly, which means I am going to be specific about where the explanation stops, rather than waving at a general sense of mystery. There are 4 places. They are all load-bearing. The first is that nothing tells us what the action is. Everything tonight has been about what to do once you have an action. You make it stationary, and the dynamics come out. That machinery is exact, universal, and beyond dispute. But it is a procedure with an input, and physics has no theory of the input. Nobody can derive the Lagrangian of a pendulum from first principles. Nobody can derive the Lagrangian of the electromagnetic field. Nobody, most pointedly, can derive the standard model Lagrangian, the one on the coffee mug, the one containing every particle we have ever detected. The way those expressions are actually obtained is this. You decide what symmetries you think the world should have. You write down the simplest expression that respects them. You compare its predictions to experiment. If it fails, you adjust it and try again. That is not a derivation. It is educated guessing, refined over decades, checked against nature, and it has worked spectacularly. But the guessing leaves fingerprints. The standard model Lagrangian contains 19 numbers that the theory does not predict: the masses of the quarks and the electron and the muon, the strengths of the forces, the angles describing how particles mix into one another. Include what we now know about neutrinos, and the count rises to somewhere around 26. Each of those numbers has to be measured and then written into the action by hand. The action principle tells you what to do with them. It has nothing whatsoever to say about why they are what they are. The second place is more uncomfortable, because it sits underneath the beautiful resolution we just built. Feynman's picture explains why classical objects follow stationary paths. It does that by assuming that each path contributes a rotation, and that the angle of the rotation is the action divided by h bar. Nothing explains that assumption. Why should each path contribute a rotation at all? Why should the angle be the action rather than some other quantity built from the path? Why should the relationship be that particular kind of function, and why should it be simply proportional rather than something more complicated? Dirac wrote corresponds to. Feynman upgraded it to a working rule, and the working rule produces correct answers about the physical world to more decimal places than almost anything else in science. But upgrading a correspondence to a rule is not the same as explaining it. It is deciding to stop asking. So we have explained why the principle of stationary action holds for large objects by assuming a deeper principle about quantum phases, which is exactly as unexplained as the thing it explains. The mystery did not dissolve. It moved down a floor. It is still in the building. The third place is that the mathematics is not actually rigorous. This one is not widely advertised outside of mathematical physics, and it should be. The sum over paths, as we described it, requires adding up contributions from an infinite dimensional space of curves. To do that properly, you need a measure, a mathematically coherent notion of size on that space, telling you how much each region of it counts for. For the version of the path integral used in real time, no such measure exists. It was proved not to exist. Physicists get around this by performing the calculation in a mathematically fictional world, where time is treated as an imaginary quantity, where a proper measure does exist, and then rotating the answer back to real time at the end. This procedure works. Its results match experiment to extraordinary precision. Nobody can say in general why it should be legitimate. There is a standing prize of $1 million for putting the quantum field theory underlying the strong nuclear force onto a rigorous mathematical footing. It has been on offer since the year 2000. It is unclaimed. The framework in which we write the fundamental laws of matter is, as mathematics, not yet known to be consistent. The fourth place is a hole in the formalism itself, and it is almost domestic. Slide a book across a table, and it stops. Friction has taken its kinetic energy and turned it into heat in the tabletop. That is the most ordinary event in the world, and there is no straightforward Lagrangian for it. The variational formalism was built for systems that conserve energy, and a system losing energy to its surroundings does not fit. There are workarounds, a device called a dissipation function that gets bolted onto the outside of the equations, but it is a patch, not a term in the action. So the principle that describes every fundamental interaction in the universe does not cleanly describe a book sliding to a stop on a table. There is a defensible answer, which is that friction is not fundamental. Zoom in far enough, and there is no friction, only enormous numbers of particles interacting by conservative forces, each of which has a perfectly good action. That is almost certainly correct. It is also an admission that the formalism only works at the level where you cannot use it for anything practical. It is worth saying that physics does have one genuine, derived restriction on what an action is allowed to look like, and it is a warning rather than an explanation. In 1850, a mathematician working in St. Petersburg, named Mikhail Ostrogradsky, proved that if you write an action depending on acceleration or anything higher, rather than just position and velocity, the resulting system has no lowest energy state. It can always find a way to fall further, without limit. Such a universe tears itself apart. So we know something about actions that are forbidden. We still know nothing about why the permitted ones take the specific forms they do. I should also flag something you will run into if you go looking, because it circulates widely, and it needs a label. There is a real and serious research program that borrows variational mathematics for use in biology, modeling how nervous systems process information, how metabolisms allocate energy, how organisms behave under constraint. That work is legitimate and productive. There is a much larger body of popular claim built on top of it, asserting that the physical principle of least action explains life itself, or purpose, or consciousness. It does not, and nobody has shown that it does. Using variational mathematics as a tool in biology is standard practice. Claiming the action principle causes living behavior is speculation, and it should be treated as such. And underneath all four of these sits the thing that has not moved since 1744. There are two descriptions of the physical world. They are mathematically equivalent. Each can be derived from the other. They agree on every prediction about every measurable quantity, to every decimal place, forever, and they describe completely different universes. I want you to look at both of them. Here is the first. A ball leaves a hand. At each instant, it has a position and a velocity, and a force acts on it, and that force determines how the velocity changes over the next infinitesimal moment. Then the same thing happens again, and again. There is no plan, there is no destination. Nothing anywhere in the system has any information about the future or about anything more than one instant ahead. The universe grinds forward, blind and local, computing the next moment out of this one, and the arc appears as an accumulated consequence of a billion tiny blind steps. Nothing has been decided. Nothing was ever aimed anywhere. Now here is the second. The same ball leaves the same hand, but the object under discussion is not the ball at an instant. It is the whole arc, laid down complete, from the leaving to the landing, a single finished thing existing all at once. And of all the complete arcs that could have connected those two moments, this one is real because the action along it is flat. The history is the fundamental object. The instant is a slice through it. Same ball, same numbers, same prediction. Two incompatible pictures of what is happening, and no experiment that has ever been proposed could distinguish them, because they are the same theory. Physics has spent 3 centuries writing every law it possesses in the second language, while quietly insisting that the first one describes what is really going on. That is a preference. It has been dressed as a result for a very long time, and it is not one. At the beginning of tonight, I gave you a sentence before you knew what it meant. For any motion you care to describe, there is a number attached to the whole journey, and the journey that actually happens is the one where that number stops changing. You know what the number is now. You have watched Newton's law fall out of it, watched electricity and gravity and the interior of the proton turn out to be written in the same one line, and watched the quantum world explain why the rule holds at all, and nobody can tell you why the number is that number. That is the honest position, not a gap in the data, not a measurement waiting to be made or an experiment somebody has not yet funded. A gap underneath the entire structure, which every physicist working today steps over on their way to work, and which has been there since a French mathematician guessed at a quantity in 1744 and was ridiculed across Europe for it. Nature is not being economical. Nature is standing still, and we have no idea why standing still is the thing it does. I find that oddly comforting rather than frustrating, and I will tell you why. The most successful idea our species has ever had is one we do not understand. We found it, we can use it, it has never once failed us, and it is still holding a secret. There is something reassuring about a universe that hands you a working key to every door and declines to tell you what the key is made of. Thank you for spending this time with me, following one rule from a ramp in 1696 all the way down to the bottom of physics. If this kind of slow walk through an old idea is something you value, a like or a subscribe would mean a great deal. It genuinely helps me keep making these. And remember, the next time you watch something fall, every path it could have taken is happening, and all but one of them is quietly erasing itself. Good night, and may you never look at a thrown ball the same way again.